Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. I bid to everyone. I am Shafina Ahmad. Today I am going to present my research paper titled The Unique Eccentricity of a Prolate Spheroid based on its depolarization factor. So first of all, I am from Department of Mathematical Sciences, University Technology Malaysia Skudai, and I am representing my team member to present our work on this study. In this presentation, it consists of introduction, objective, literature review, methodology, result and discussion, and lastly, conclusion. First, introduction. In the presence of a uniformly applied field, a body is magnetized by both the applied field and also its own magnetic field, which is produced as a result of its own magnetic pole. The field is often called as the depolarization factor created by the magnetic pole, which is represented as Di in this equation. Magnetization of the irregularly shaped material in a uniformly applied field is likely to cause the total field throughout the material and the surrounding of the material to change in magnitude and differs in direction. So, as a consequence, this making it difficult to measure the magnetic force produced by the material. Magnetic material usually present this kind of difficulty because most of the study are need to find the link between the magnetization and also magnetizing force. So for that reason, data on some magnetic material have to be corrected by taking the depolarization factor into consideration. Next, tensor known as polarization tensor or PT is commonly associated with depolarization factor that can be related to each other. It has been used in a variety of applications, and the implementation of PT in enhancing the identification of objects can be seen, for example, in the study of electrosensing fish. This weakly electric fish is used in the application of PT in order to navigate the object, where this fish actually generate current from its electric organ at the base of the tail, and it also have thousands of receptor cells over the fish body. And the second one is metal detection in detecting mine, and also walk through metal detector as we always see in airport. And lastly is the biomedical imaging, for example lung scanning, in detecting the normal and also abnormal tissue. Proceed with the objective of this study. First is, we want to identify the trend graph of the depolarization factor, either it is increasing or decreasing for prolate spheroid. Next is to investigate the limits of depolarization factor for prolate spheroid in between 0 and 1. And the last one that we are concerned is to prove that the depolarization factor of a prolate spheroid has a unique eccentricity. For literature review, at first, Thomson and Tate gave a definite integral formula in 1895. Later on, Osborn then studied the depolarization factors of the general ellipsoid and gave a simpler formula of the depolarization factor by using the elliptic integral. And in the same year, Turner introduced the general integral formula for the depolarization factor of an ellipsoid with some additional factors. And the formula of the depolarization factor are then derived by Maxwell in 1954 during the study of the potential problem. He actually derived the formula from Thomson and Tate. And later on, Milton had shown that the depolarization factor are also equivalent to the classical integral in 2002 when studying the theory of composite. And actually, the study regarding the depolarization factor actually is not limited to the spheroid or ellipsoid only, but there are a few studies for other geometry as well, such as cylinder and also rectangle. However, Belligia in 2006 proposed that any difficult or any complex shape can be equivalent to an ellipsoid by considering its depolarization factor. Then, in 2019, Muhammad Yunus gave some properties of depolarization factor related to the ellipsoid. Next is about the background of the depolarization factor. The integral formula of depolarization factor for ellipsoid in Cartesian coordinate where A, B, and C here are the semi-axis is defined by this formula of D1, D2, and D3 in the direction of X, Y, and Z axis. In general, these equations are the classical integral which can also be expressed as elliptic integral. It can also be expressed as triplet D1, D2, D3. So this is how ellipsoid looks like with semi-axis A, B, and C. Furthermore, some properties of the depolarization factor for ellipsoid can be stated as mentioned in Proposition 1, Proposition 2, and also Proposition 3, which are necessary in this study. It is stated that the depolarization factor are non-negative number or positive number. The total of depolarization factor D1, D2, and D3 are 1. And lastly, the depolarization factor are between 0 and 1. Apart from that, the explicit formula for D1 can be reduced to a simpler formula. The formula is only applicable for two cases when the ellipsoid is either prolate spheroid, where the semi-axis are A greater than B equal to C, or oblate spheroid, where the semi-axis are A less than B equal to C. So these formula are shown in proposition 4, where phi and also verified in this equation here are known as eccentricity. In this paper, we actually want to determine that phi for Prolate spheroid is a unique solution to the function of D1. Next is the methodology. The methodology can be summarized into this flowchart where we start with literature review of the depolarization factor. Then we found out the trend graph of the depolarization factor for Prolate spheroid, either it is increasing or decreasing function. Next, we determine the limit for Prolate spheroid regarding its depolarization factor and prove that it has a unique eccentricity of our last finding in this study. Next, this is the result that we defined in Theorem 1. First and foremost, we need to show that D1 is a decreasing function. So, let A, B, and C represent the semi-axis, and D1 is the depolarization factor. D1, which is equal to this formula for Prolate spheroid, is a decreasing function. To prove this, first we must show that the derivative is always negative for phi in 0, 1. Since 2 phi power 4 here is positive, then we let this function f phi to become negative. But before that, we find the critical point of the function. After compute for critical point, we found that the function is 1 to 1 and there is only one critical point, which is 0. Then, to show that f phi is less than 0, we find the limit when phi is approaching to 0 and 1. Therefore, we obtain that when phi is approaching to 0, the limit of f is 0, and when phi is approaching to 1, then the limit of f is negative infinity. That conclude that f phi is less than 0 when phi is between 0 and 1. Hence, the derivative of d1 is less than 0, which implies that d1 is decreasing for phi in 0 and 1. Next, for theorem 2, d1 for Prolate spheroid, where A is greater than B equal to C, satisfies 0 less than d1 less than 1 over 3. So, in order to prove this, finding the limit for d1 is necessary. Firstly, we compute the limit for d1 when phi tends to 0 by implementing the limits law and also by using L'Hopital rule. Then, we obtain that the result when phi approaching to 0 is 1 over 3. Next, we determine the limit of d1 when phi tends to 1. Then, we obtain that 0 is the limit for d1. Hence, it is concluded that d1 for Prolate spheroid satisfies 0 less than d1 less than 1 over 3. Last but not least, for corollary 1, d1 for Prolate spheroid, where A is greater than B, has a unique eccentricity phi, where in this case, we want to find out there exists a unique phi for phi in 0 and 1 for the function of d1. So, to prove this, we refer to the previous theorem 1 and also theorem 2, where d1 is decreasing and it is between 0 and 1 over 3. Therefore, D1 is said to be monotonic since it is strictly decreasing. Since D1 is strictly monotonic on phi in 0, 1, we can say that D1 is 1 to 1, which conclude that this D1 has unique eccentricity. So this following straightforward result is very useful to determine that D1 exists a unique eccentricity by referring to theorem 1 and also theorem 2. In conclusion, this paper shows that D1 for Prolate spheroid is a decreasing function. So how about D2 and also D3? Since for Prolate spheroid B is equal to C, then D2 is actually equal to D3. Next, the value for D1 of Prolate spheroid must actually be between 0 and 1 over 3. And last but not least, since D1 is strictly monotonic decreasing, then D1 is 1 to 1, which conclude that D1 has a unique eccentricity. For recommendation, a similar technique can also be applied to identify the depolarization factor for oblate spheroid where A is less than B equal to C, and it is assumed that D1 for oblate spheroid is an increasing function. That's all from me. Thank you for listening.